Well, hey folks, this section we're going to start looking at functions of several variables, and here are the objectives we're going to check out in this section. We're going to see how to evaluate a function of two independent variables, and once we know how to do that, we'll look at an application where we will determine a cost function of two independent variables. And then we're going to look at how one would go about plotting points in what's called three space. And we'll take a quick look at graphs of planes in three space. And our fifth and final objective will be very business specific. It's a look at analyzing a cobb-douglas production function. All right, so with that said, let's get the show on the road here. First off is, let's call this a definition of a function of two independent variables. If you have any equation that's in the form z equals f of xy, and that's how I would read it, z equals f of xy, that represents a function of two independent variables. If for each ordered pair or real numbers x, y, the equation gives us a unique real number z. So x and y are the independent variables here, folks. Z is the dependent variable. And well, we have that label mentioned here. Variables x and y are independent, and z is the dependent variable. Very important for you to remember that. And then, once we start talking about functions, it's natural for us to talk about domain. So here I'm just going to quickly say, for a function of two independent variables, x and y, the domain is nothing more than the set of all ordered pairs x, y, for which z is defined. So just remember basic things about domains of functions, folks. You can't divide by 0. You can't do the square root of a negative number. You can't take the log of a negative number. Those things still apply here, so nothing has changed. So let's take a look at a quick example. Let's consider this function. Function of xy equals 2x plus square root y. And we're going to determine in part A the f of 3, 4, and in part B the f of 1, 25. So this is old school evaluating a function. So what I'm going to do now, going to head off to the chalkboard and work through this example. So make sure you have it written down because here we go off to the chalkboard. Hey folks, this example we left off with, we were given f of xy equals 2x plus square root y, and we were asked to evaluate the f of 3, 4 and the f of 1, 25. This is just like old school evaluating functions. We see 3 is in the place of x, 4 is in the place of y. So to evaluate the f of 3, 4, all we do is put 3 in here wherever we see an x, and put 4 in here wherever we see a y. And let's see, 2 times 3 is 6, square root of 4 is 2, we get 8. The f of 3, 4 is 8. So for part B, same deal. X is 1, y is 25. So we put 1 in for the x, and we put 25 in for the y. 2 times 1 is 2, square root of 25 is 5, and 2 plus 5, we're going to go with that being 7. So that's it. That's all there is to it, to evaluating functions. This is an important skill. It's like one of the main skills we're going to focus on here in section 8.1. So because it's so important, I'm going to want you to pause the video and try number 13. And after you've done number 13, restart the video. I'll be here working through the solution at the chalkboard. All right, and number 13, you were given f of xy equals x squared plus y squared over x plus y. And you were asked to evaluate the f of negative 2, negative 3. So hopefully what you did was you put negative 2 in wherever you saw an x, and you put negative 3 in wherever you saw a y. So that would give you a negative 2 squared plus a negative 3 squared over a negative 2 plus negative 3. See, that's 4 plus 9 And then negative 2 plus negative 3 is negative 5. So that's 13 over negative 5. I think it's better to write that as negative 13 over 5. And hopefully you got that for 13. So what we're going to do now is we're going to head back to the slides and we're going to look at an application, and then we'll be well on our way. All right, hopefully you saw that evaluating functions of two independent variables was pretty friendly, and hopefully you were able to crank through number 13. So next up, the next example we're going to look at is going to be a very quick, it's going to be an application. So this establishment called Cuppa-Cupcakes, they make gourmet cupcakes for special events. Their red velvet swirl costs $1.27 per cupcake, while their lava chocolate costs $1.45 per cupcake. Part A, we're going to determine a cost function C, and this is going to be a function of x and y, two independent variables, where x is the number of red velvet swirl cupcakes and y is the number of lava chocolate cupcakes. See, it seems kind of natural. We have two different types of cupcakes. It seems natural to use two variables, one to represent each type of cupcake. After we do that in part B, we'll determine how much it costs to make 1 dozen of the red velvet swirl and 2 dozen of the lava chocolate cupcakes. So hopefully, write this example down, because you know the drill. I'm heading off to the chalkboard to work through the example. All right, hey, this example we left off with, it said, Cuppa-Cupcakes makes gourmet cupcakes for special events. The red velvet swirl cupcakes is $1.27. It costs $1.27 per cupcake, while the lava chocolate costs $1.45 per cupcake. In part A, we're going to determine a cost function. Determine a cost function C, and it's going to be a function of x and y, a function of two independent variables, where x is the number of red velvet swirl cupcakes and y is the number of lava chocolate cupcakes. So let's just think about this for a minute. If it costs $1.27 for each of the red velvet swirl cupcakes, then if we are getting x to represent the number of red velvet swirls, then that means the cost just for the red velvet swirl would be $1.27 times x. Now for the lava chocolate, they cost $1.45 per cupcake. So if we are letting y representing the number of lava chocolate cupcakes, then the cost for those y number of lava chocolate cupcakes will be 1.45 times y. So this is the cost for the red velvet swirl. This is the cost for the lava chocolate. To determine the total cost, we should take this cost for the red velvet swirl plus the cost of the lava chocolate. And it looks to me like that is nothing more than the cost function as a function of x and y. So the cost function C is a function of x and y, where x is the number of red velvet swirl cupcakes and y is the number of lava chocolate cupcakes. That cost function as a function of x and y is just 1.27x plus 1.45y. Then in part B, when you're asked, how much does it take, or how much does it cost to make 1 dozen red velvet swirl and 2 dozen lava chocolate cupcakes? Well, 1 dozen would be 12. So really you're being asked, how much does it cost to make 12 red velvet swirl and 2 dozen, that would be 24, so 24 lava chocolate. So what's the cost for 12 red velvet swirl and 24 lava chocolate? That's the same thing as saying evaluate the cost function at 12, 24. And quite simply, just as we've seen so far, we put 12 in for x, 24 in for y. So
And before I crank this through my calculator and get an answer, this little piece right here, that tells me the cost for the 12 red velvet swirl cupcakes. This little piece here is the cost for the 24 lava chocolate. So of course we would add those two costs together to get the total cost for all these cupcakes. And when I crank this through my calculator, I get a cost of $50.04. Must be really good cupcakes. All right, so now we're going to head back. We're going to look at some slides. We're going to look at some slides, on what's happening here geometrically. After we, looks like we're going to look at a few slides. We'll come back to the chalkboard and we'll do another example.
All right, hey, hopefully that example made sense and you saw, this stuff is looking pretty friendly. Kind of switching gears here momentarily. Now that we're working with functions that have two independent variables, folks, we're going to take a quick look at how to plot their points. So there will be a value for x, a value for y, and a value for z. For that reason, they're called ordered triples, and they're of the form x, y, and z. And when we plot these points, we plot them in 3 space, so it's 3 dimensions. So we're going to have three axes. We're going to have an axis, an x-axis. We're going to have a y-axis, and we're going to have a z-axis. And our 3 axes, they're all going to meet at right angles to each other. And where they meet, we're going to call that point, well, we're going to call it the origin. So that's kind of new. It's not new. It's still the same. And the origin has coordinates of 0, 0, 0. So the first thing I'd like to look at here, and I think you'd see this in your textbook, figure 8.1.1. That's a generic coordinate system. There's the x-axis, the y-axis, and the z-axis. What I'd like to point out in the XYZ coordinate system, notice the positive part of each axis is solid. The negative part of the axis would be the dashed part. The other thing I'd like to point out is we know when we had 2 variables, x and y, and we made a coordinate system, we had 4 quadrants. We no longer have quadrants, we now have octants. We have 8 regions. There are 4 regions that's above the xy plane and 4 regions that are below the xy plane. And now I'm going to switch over to look at figure 8.1.2. Notice here, I've instructed someone to kind of draw a room to help us visualize the XYZ coordinate system. Folks, I would like you to visualize the XY plane, what you've been doing all of your graphs on. I want you now to consider the XY plane to basically be the floor. And then, the z-axis is drawn here as kind of going up one of the corners of the room. But this can help you visualize that there are 8 regions. There are 8 octants. There are 4 regions that would be above the floor and 4 regions that are below the floor. So that's the total of 8 regions. And you're going to hear me talk about this in class as well. I always think of the XY plane as being the floor. It is the floor. We can see there are 4 quadrants on the floor. 4 regions that are above the floor, 4 regions that are below the floor. So now that we've looked at the axes, when we graph a function of 2 variables, now folks, I'm not going to do this in class. I am not going to ask you to do this because it's very difficult to draw a 3-dimensional object on a 2-dimensional surface. Whenever I make a graph on the board, that's a 2-dimensional surface. It's very difficult to draw these things, but I do want you to know that the graph that's taking place in 3 dimensions, I'd like you to know that it's called a surface. And, quite simply, it's just a collection of points, x, y, and z, where z is the f of x, y. So z is the dependent variable, and x, y are the independent variables. Very difficult to graph these things. If I really wanted to do graphs of these things, I would most definitely be using computer software to graph these surfaces in space. Now, the easiest or most basic of these 3D graphs are called planes. And they quite simply, they occur when one of the variables is constant. And they're kind of analogous to a horizontal or vertical line in 2D, or when we're graphing just in the XY coordinate system. So it's kind of analogous to that. What I am going to say now, and I haven't done it yet, this year, but example 4 on pages 632 to 633 shows you how to plot points. So please consult example 4. What I'm going to want you to know about this, and make note of this, when you see an ordered triple, I want you to be able to identify that the z-coordinate is telling us if we are above the floor, the xy plane, or if we are below the floor, the xy plane, or even if it's on the floor. So think about what that means. If you have an ordered triple xyz, if the z-coordinate is positive, you're above the floor. If the z-coordinate is negative, you're below the floor. And if the z-coordinate happens to be 0, well, you're not above the floor, you're not below the floor, you are on the floor. But please consult example 4 on pages 632 to 633, and then give a look at example 5 on pages 634 to 635 on graphing planes. I'm going to be looking at very specific planes that I'd like you to know. So moving on to the next slide. When only one variable appears in your equation, a plane that is parallel to one of the coordinate planes is going to result. So here's what I really want you to know. We have 3 coordinate planes. The xy plane, that's like the floor. The xz plane, that's like one of the walls. And the yz plane, maybe that's like the front board in the classroom. When we graph planes that are parallel to these coordinate axes planes, well, you're going to get the following scenarios. The graph of z equals c. C is any number, folks. That's going to be parallel to the xy plane. For example, the graph of z equals 5. That means you are looking at all points that would be 5 units above the xy plane. So all units that are all points that are 5 units above the xy plane, that would give you a plane that is parallel to the xy plane. It's a plane that is parallel to the floor. The graph of x equals c, well, that's going to be parallel to the yz plane. So in other words, if you graph the plane x equals 5, you're plotting all points that would have an x coordinate of 5. And it's going to be parallel to, well, the board. I always consider the board in our classroom to be the yz plane. And finally, the graph of y equals c, that's parallel to the xz plane. So if c has a value of 5, the graph of y equals 5 is you're plotting all points that are 5 units away from the xz plane, and I always consider the xz plane to be one of the walls in the classroom. Quick picture, and this is just a picture from your book as well. Figure 8.1.9, part A, that's the graph of the xy plane. And again, I like to think the xy plane is the floor. Part B is the graph of the xz plane. And I like to consider the xz plane to be one of the walls in the classroom. Part C is the graph of the yz plane. And I like to consider that to be the front of the room, or the chalkboard, or the marker board, the whiteboard that's in the front of the room. So if I ask you to graph, and I wouldn't, but if I ask you to consider the graph of z equals 4, it's going to be a plane that is parallel to the floor, but it's just going to be 4 units up. So it'd be a plane, and I can't draw a plane here, but it's going to be parallel to the floor. Hopefully that makes sense. So moving on. We're getting into the cobb-douglas production function stuff now, folks. Think about when you produce any item, say a baseball bat, one of these fancy aluminum baseball bats. There are many inputs that are used in the production process. Many inputs. In business, well, we're going to tend to let Q represent the output. So the output Q, baseball bats say, is a function of many variables. And notice here I'm labeling them as x sub 1, x sub 2, x sub 3, comma, yada, 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 x sub k, where all of those different x subs is a different input. There are a lot of inputs that go into making an item. You need materials. You need electricity. You probably need a heating source. You need a building. I mean, building, there's going to be, you either own the building or you're renting the building. You have to have insurance on the building. You need employees. You got to pay employees. I've just rattled off a lot of inputs. In practice, econ folks call Q a production function. And in practice, what they say, there are so many inputs, we're going to collapse these inputs down to just 2 inputs. They collapse all these inputs down to 2. L, which represents labor, and K, which represents capital. So all of those things that I just babbled, and it was a small number because there are a lot of inputs that go into making an item. All of those get collapsed down to just 2 inputs, labor and capital. And they like to say that a production function Q is going to be a function of just 2 inputs, a function of labor and a function of capital. Well, along came these 2 dudes. Cobb was one and Douglas was another. One of them was an econ guy and the other one was a mathematician. They kind of came up with a production function. And this is basically it. They said if L represents the units of labor and K represents the units of capital, then total production Q can be given by, well, it's called the cobb-douglas production function. I mean, they named it after themselves. And that it has the form Q equals A times L to the B power times K to the C power. And here A, B, and C are constants. Let's look at an example of a cobb-douglas production function. So let's say there's someone out there making tablets, and they have a cobb-douglas production function given by Q equals f of xy equals 18x to the 0.65, y to the 0.35. And here in this cobb-douglas production function, x is the utilization of labor, and y is the utilization of capital. So what are we going to do in this example? Ooh, cool. Part A, we're going to determine the reasonable domain of this cobb-douglas production function. And then in part B, we're just going to determine the number of units of tablets that are produced when there are 200 units of labor and 75 units of capital being used. So you know the drill. Make sure you have this written down because I'm going to head off to the chalkboard to work through this example.
All right, folks, we just looked at a lot of slides, try to get a handle on what's happening here geometrically, and I asked you to consult some figures in the textbook and a couple of examples in the textbook. And then our last slide before we got here to the chalkboard dealt with a very special type of function of 2 variables that's used in business, and it's called the production function, specifically the cobb-douglas production function. So here is an example where in the example we saw that a tablet manufacturer had a cobb-douglas production function given by Q equals f of xy equals 18x to the 0.65, y to the 0.35. Remember Q is the quantity that's made. X was utilization of labor, and Y is utilization of capital. And part A is just what is the reasonable domain for this function of two variables. So folks, if X represents utilization of labor and Y represents utilization of capital, it isn't reasonable for X to be a negative number, and it isn't reasonable for Y to be a negative number. Now we could say X could be 0. It's not going to be too good for this manufacturer. If they use 0 units of labor, they're not going to make anything. Y could be 0, and that's not going to be good for the manufacturer either. If Y is 0, so they use 0 units of capital, they're not going to make anything. I mean, if X is 0, this product is 0. If Y is 0, this product is 0. But that could happen. It is in the, quote, reasonable domain. But negative values for X, negative values for Y are not reasonable. So for that reason, I would say the reasonable domain is all values of X that are greater than or equal to 0, and all values of Y that are greater than or equal to 0. Now I'd like you to know what this means graphically. Graphically, now remember when we're talking about these functions of several variables, we have an x-axis, a y-axis, and a z-axis. Or here it would be the q-axis. So there are 3 axes here. So what I would like you to know is when x is greater than 0 and when x is greater than or equal to 0 and y is greater than or equal to 0, you're restricted to looking at what's happening in quadrant 1. Quadrant 1, that's where x is greater than or equal to 0 and y is greater than or equal to 0. And I really want you to kind of know that. For all these production functions, this is what the reasonable domain is going to be. And then the graph of that, which we'll just look at pictures in the book, is going to be a surface that is above quadrant 1 in the XYZ coordinate system. So reasonable domain, x greater than or equal to 0, y greater than or equal to 0. This matches up with quadrant 1 in your XY coordinate system. And remember, when you have 3 axes, you actually have octants. There are 8 regions. But I'm just here talking about the XY plane. That's it, the XY plane. The floor. Consider the floor to be the XY plane. And this would be quadrant 1 on the floor. Part B. Part B is determine the number of units of tablets that are produced. I just wrote it down, units made, when 200 units of labor and 75 units of capital are used. Well, X is labor, Y is capital. So that is X, that is Y. So really, for this problem, you're being asked to evaluate your function, xy. You're being asked to evaluate it at 200, 75. So you just, old process, you just toss 200 in for the x. That's a 0.65 exponent. 75 in for the y. And boy, I'm so happy to have a calculator here. When I crank this through my calculator, I get 2,553.956, which I would just round it to 2,554. About 2,554 units of tablets can be made when 200 units of labor and 75 units of capital are being used. We're going to do a lot of work in this chapter in the next few sections dealing with this cobb-douglas production function. And so one of the most basic things we could do right now with the cobb-douglas production function is just simply evaluating the cobb-douglas production function. So to make sure you have it under control, I'd like you to pause the video and do number 75. So go ahead, pause the video, do number 75. When you're done with 75, restart the video, and I'll be here at the chalkboard cranking through the solution. All right, hey folks, here number 75, it says a sports shoe manufacturer has a cobb-douglas production function given by Q equals f of xy equals 42x to the 0.37, y to the 0.66. And here x is utilization of labor, y is utilization of capital. And we're asked to determine the number of units of determine the number of units of sports shoes, I almost said golf clubs there, I was looking at the wrong one, produced when 300 units of labor and 100 units of capital are used. Alright, so X is labor, Y is capital. How many sports shoes are we making when we use 300 units of labor and 100 units of capital? Well, that's just simply evaluating your production function at 300, comma 100. X has a value of 300, Y has a value of 100. So, as we've seen so far in this section, we toss the 300 in for X, toss the 100 in for Y, and be very happy that we have a calculator to do the calculations here. And we get something pretty close to 7,240.76. I would actually say the answer is 7,241 units. I would round it to the nearest unit because we're talking about shoes here. No one wants 3/4 of a shoe. So hopefully you got that for number 75, and hopefully you're saying, hey, this is pretty friendly stuff. Just evaluating functions, that's it. We're going to head back to the slides. I just have one more informational slide, and that will conclude this section after one more informational slide, and then you should be good to go on doing the homework in section 8.1.
All right, hey folks, hopefully you saw how friendly this is. Hopefully it made sense what the reasonable domain happens to be. Part B, hopefully you saw, hey, this is old stuff now. We're just evaluating a function. At 275, it was just basically evaluating a function, and hopefully you were able to do number 75. But as I said, there was one more slide I wanted to look at, and it deals with Cobb and Douglas. When these dudes first introduced their production function, it had the form of Q equals A times L to the B power K to the 1 minus B power. So in other words, look at the exponents. One exponent is b and the other exponent is 1 minus b. So when they first introduced their production function, the sum of the exponents was 1. And the reason why they used this form was they were restricting their results to what is referred to a constant return to scales. And that's very econ-ish. I just wanted to bring it to your attention. And I do want to make one more note that in their form, the exponents added up to 1. All right, so that kind of concludes this video, folks. Make sure you look at the section, look at the objectives, particular attention to the graphs. I would like you to know for the Cobb-Douglas production function, the reasonable domain is x greater than or equal to 0, y greater than or equal to 0. That's quadrant 1 of the xy plane, because then we're going to be looking at what the graph looks like of a production function. We'll be looking at figures in the textbook, and I want you to know that it's just living over quadrant 1 on the floor. But that's it. Hopefully you have a good time with the homework in section 8.1. It's kind of calculus free right now, but that'll be changing soon. So go ahead and do the homework, and thanks for watching.